Good evening, everyone. Today is the first class of the course Optimal Design of Queuing Systems. Uh, I'm Aniket Mukherjee. I'll be taking the class. Um, Basically, what we'll see in this course is how do we design queuing systems, and so we'll have two parts. So one part would be the design of the queuing systems, and the other part would be the control of the queuing systems. So both have the same they're almost similar in the meaning but have a slight variation in how I would define design and control. So design would be something where you have a queuing system, and all the parameters of the queuing systems are same. Now you design or you choose a parameter which is optimal so that your required performance, your queuing system performs in a manner that you design. Whereas in control, what we'll have is we'll have feedback, or we'll assume some distribution or some probabilistic statistical data, how the queuing system is performing, and based on those statistical data or even the feedback, we'll try to design, mm, or we'll try to find the parameters that suit the queuing system. So, okay. First, in this course, we'll follow two textbooks. One textbook would be Optimal Design of Queuing Systems, and the other book is Stochastic Optimization with Applications to Communication Queuing Systems. We'll go back and forth in both of these books because one book deals with design part, the other book deals with control part. Right. So some basic prerequisites that we need for this course is basic probability. So what I'll do is, instead of doing 2-3 classes on introducing probability and what all stuff we'll need for the course, uh, uh, as the course progresses, anywhere you need any probability stuff, I'll just introduce it and then um, come back to the core material. Uh, a little bit stochastic process because we'll be designing MM1's queues, and similarly, um, yeah. So some stochastic process because we'll be modeling arrival process, service processes with Poisson process. So those are the prerequisites. So some prerequisites are um, basic probability, right, and stochastic process, a basic idea on what a queuing system is, and elementary calculus. Okay, so uh, first I'll start the today's lecture by giving an introduction on what we'll do. So basically, what you have. So first I'll introduce a queue. So queue, you have a service component, and you have a queue component, right? And then you have arrivals, and you have departures. So you have some random customers or jobs that arrive to get served at some place or anything. So we we usually model the arrivals. So we need to model this. So what we need to do is we need to parameterize the arrivals, right? Then you have your service. So this service, uh, so when the customer queues up to the server, the server provides the customer service. Now each customer or each job could have different requirements. So based on the requirements, the amount of time the server provides the service differs. So again, uh, this is your service, and this is also modeled using random. uh, or some statistical measure. We'll we'll see. So similarly, we parameterize the arrivals. We also parameterize the service. Now, these both are the uh, basic uh, things that you. If you define these two, if you parameterize these two, then you're basically defining a whole queue. So the queue basically states that you have some arrivals happening at some random rate, right? You have a server which serves at a random rate. Now, given these two, you can find different things of how is my queue length trajectory. So how does this queue build up, right? How at what time, how many mm, per people do I see in the queue and so on? At what rate do people departure given the service rate and so on? So yeah, so basically what we have is we have arrival rates, service rates, right? Then inter-arrival distributions, inter-service distributions. So whenever I'll talk about arrival rates, I'll be depicting it using lambda. Whenever I talk about service rates, I'll be depicting it using mu. Inter-arrival distributions, for the most simplest case in the starting, we'll be dealing with exponential distributions. Similarly, the inter-service distributions also will be using exponential distributions. Next, we'll have the queue disciplines. So in the queue disciplines, you'll basically get a scheduling policy. In the scheduling policy, we'll see. Uh, the design part is either you can fix the scheduling policy and then find out lambda mu. So there are multiple ways you can go through the design process. We'll look at all those cases. Scheduling policy is something where you see multiple customers arriving. Now the server has a decision to make. The decision that he makes is who am I going to serve first? So if he says that, okay, I'll serve the first customer who has come, I'll serve him first, and then I'll serve the next customer, then it's something known as FIFO. But then if the server is telling that he has a mind, he thinks that no, I'll not serve the first customer who has come, I'll serve the customer who will be very quick to serve, so who has very less requirements. So shortest job first, something like that. Or you might also say that, okay, I have a premium customer who has come to get service from me. I know he'll pay me more, so mm, I'll mm, I'll I'll serve that guy. So something of those sort. And then you have random server. So the server doesn't care who or what has come at what time. He just picks a customer randomly from the queue and then he starts serving the customer. Right. So we'll try to come up with random scheduling policies, and also we'll try to come up with different types of scheduling policies. In the random, we'll come up with, okay, yeah, he goes with random, but what is the distribution that he has to follow, right, to meet some certain criteria or requirements of your queuing system. So we'll look at all this, right? So yeah. Okay. So in addition to this, the queuing systems that we are going to study, uh, they may not be a simple representation of. So this is a simple representation of a queue, right? Simple representation of a queue. Your queue might not always be a simple representation. You could have multiple servers. You could have multiple queues. You could have multiple queues, single server. You could have single queue, multiple servers. You could have a network of queues, right? or you could have different class of customers arriving to the same queue, different class of customers arriving in different queues. Um, so that also specified before once you, so these all things are, uh, so based on which application you're trying to apply this theory to, you'll have to model it based on that. So those are also a type, those also will take into consideration, right? And okay, so what do I mean when I say that I'll be doing optimal design of queuing system, right? So when I say optimal design of queuing system, when you're doing design of anything, some parameters are subject to decision making, right? So you have some decision making component because you're designing. You have to take a decision on mm, what the parameter that you're designing it, what it should be. And the decision that you make can't be any random decision. The decision is made with some explicit attention to some consideration. That consideration could be an economic consideration or customer requirement consideration, some consideration that you need to. So the uh, there should be some consideration. We will uh, technique. So we will give terms for these things later. But first, I'm just introducing the what goes into design of query system. So some consideration you need to make while taking the decision making process, right? And using these considerations and the customer requirements and all or requirements that the queuing system needs to fulfill, right? uh, the decision maker would use these as the guiding principles to take decisions on what the parameter would be. Okay, so now let's give the names to the terms. So one is a decision variable, as the name indicates. These are the parameters which will be decided by the decision maker or you here who is designing the queuing system, right? Cost and benefits. These are the consideration, the requirements that people give to you, the design maker, the decision maker who is designing the queuing systems. Objective. So what usually happens is you get a different cost from different. So the one customer would give you some type of cost. A service provider or an internet provider could give you a different type of cost. You would have different mm, considerations in his mind. A customer would have different consideration. A customer would think that, okay, I want to get served quickly. But whereas an internet service provider, he could think that no, I don't care what my individual customer uh, sells, uh, but I want more money to be generated in a short amount of time. Now, this is it would so there are two types of things. Now you need to combine these two requirements and form an objective. The objective is what gives you mm, the objective is what you take all the considerations that you get and you formulate it as an objective function, right? So the decision variables, these include um, something similar to an arrival rate, service rates, or the scheduling policies. So costs and benefits usually they come under the form of waiting times. So customers don't want more waiting times, right? Service rates or arrival rates. So more service rate you give, the more cost you have to pay. So there will be a cost incurred. So this will be a function of service rate, not service rate, but some function of service rate. But that is because you are allocating resources to serve the customer. And this has a cost that the company has to pay who is maintaining the queue. Right? And now you combine multiple type of these costs and you formulate an objective function. Okay, so how do the dynamics play a role here is suppose you are designing the service rate, right? If you have more service rate, then you'll have less waiting time. So intuitively, what happens is if you increase the service rate of the server, then you'll see that so now the service rate has increased. That means that the server gets more amount of work done in less time. So each customer will be served very quickly. So as you keep on increasing the service rate, the waiting time of each customer will decrease. So the question is, okay, so then I'll give infinite service rate and there'll be no waiting time at all. But the problem is to give infinite service rate, you're allocating that much amount of resources to give infinite service rate, and that is also a cost that comes into play. So you need to make sure that I don't over exceed my resources. So I have some minimum amount of resources that I can use. So using those, what is the best service rate I can give, right? Those are decision making process. If I give infinite service rate, then I'll be losing money or something while designing my queue, right? Uh, okay, so the nature of the objective function, it also depends on the horizon. So horizon is something which we say that till what time you want to look at the problem, right? So you have a finite horizon problem or an infinite horizon. So in the finite horizon problem, in the finite horizon problem, um, as the name suggests, you'll have a finite amount of time to make your decision. So you'll observe you'll see how does the queuing system parameters vary in the finite amount of time, and I want some outcomes in that finite amount of time, then what is the best decision that I can make in that small finite amount of time so that I get the desired requirements. Whereas in the infinite problem, what you do is you allow the system to run for infinite amount of time, and once it reaches some steady state or some distribution or some uh, requirement, then what you do is mm, you take the decision. Okay. Yeah. So today what I'll try to do is I'll try to give quick introduction to these basic components that we'll use the design model. Uh, I'll also try to illustrate some effects of different types of reward and cost functions and how we can combine them to form the objective. So while forming the objective, what you have is you'll always have a trade-off between two cost functions. So one cost function will try to increase the decision variable, and another cost function will try to decrease the decision variable. It's not always one would try to increase and the other would decrease, but you'll have some conflict. So you'll have some trade-offs. The example that we have seen before, the waiting time and service rate and arrival at allocations. So similar to that, you'll have some trade-off between those two. Right. So you can, so, yeah, as the example seen before, you can keep on increasing the service rate. But then if you keep on increasing service rate, you have a cost to pay to allocate the resources for higher service. But the more service you give, the less waiting time the customer has to pay. So that is a trade-off, right? Mm. And next, to be very simple, what we'll do is first we'll use the primary classical queuing models, right? classical queuing models, we'll basically use MM1. So what does this mean is we have exponential arrivals. Okay, so maybe not exponential arrivals. These are Markovian arrivals. Markovian circles. So when I say Markovian arrivals here, I mean it's in a continuous time. So what you get is as a result of the Markovian arrival thing, the inter-arrival distribution. This is exponential. Right. Similarly, here also the inter-service distribution. This is exponential. In this last term, this is known as this is the number of servers that you have. So we'll first deal with one server, one single queue for today at least, right? And then for today, to make it simple, we'll deal with infinite horizon problems. Now, infinite horizon problems, we can have two ways to study it, right? So one, we can just take the steady state and forget what happens in the starting in transients. We can take the steady state, and once the queue has settled to some steady state, we'll uh, yeah we will design the system. And the other is you can take a time average decision at each time step or slot. We'll talk about this later. For today, we'll deal with the steady state for the simpler. This kind of taking decision at each epoch, which we normally call as control but not design. This we will see in Neely's book or the second book that I've mentioned here. So this book would talk about control, and this book would talk about design, right? So design basically you're fixing all the parameters. You're saying that the parameters are not going to change because I'm at steady state. And now, okay, I'm at steady state. Now, what are the parameters that I need to choose so that I get my required thing? Whereas in control, what you do is I don't worry about the steady state. I know the distributions at each point of time, or I know some statistical awareness of at each point of time, or I know something else about the queue. Using those, can I make decision what is the best thing that I can do in the next step, right? Next immediate step, so that if I keep on doing that for a long amount of time, my requirements are going to meet. Okay. So for today, for the first few classes, we'll deal with the steady state design. Okay. And since we're dealing with steady state design, and we are also dealing with MM1 queues, we'll have closed form solutions for most of the cases. Mm. But then we'll not try to we will derive the closed form solutions for some of wherever we require. But right, so in the design, yeah, so steady state design and time average type design, taking decision at each for control and design. Yeah, so for now we will no, so, yeah, so we'll be using MM1Q and steady state. So we'll have closed form solutions whenever we require to derive something from the queuing systems, we'll try to derive. If it is a very lengthy derivation, then we'll just state the flow from solution, we'll move ahead, right? I'll give you basic uh, pinpoints of how to derive that thing. And once you have the basic idea of why this flow from solution works, some intuition behind it, we can skip forward, right? Okay. So let's begin the first thing, deriving optimal service rate. Okay. So first, let's put down what do we know. We know that our queue follows MM1 queue. It's an MM1 queue, right? So how do you define an MM1 queue is at what rate are your arrivals occurring and at what rate is your service going in. So we parameterize this by arrival rate. This is lambda. Service rate. This is now we have this as our decision variable. This as our known variable. So we know what our arrival rate is. We want to find what the service rate is. So what do I mean when I say arrival rate lambda and service rate mu? So I mean customers arrive according to Poisson process with parameter lambda. Okay. There's a single, so this one indicates there is a single server. This server serves the customer one at a time, right? And now the service time is independent of the arrival time. So it doesn't have any, and that process is IID. So service is IID with an exponential distribution with mean 1 by p. So the expected service time with mean 1 by p. So lambda is fixed. We know what lambda is. Now we need to find what mu should be. Right. So some examples of this is suppose you have a machine in some factory. You want to the machine how fast the machine should be. So that machine takes some input, gives some output, right? The inputs are not, they don't come at fixed times, they come random. So but you can model it using some Poisson process. Now you want to find, okay, how fast of a machine do I need to install in the plant so that I can get my required number of, so the output of the machine matches some requirement that you have in your factory, right? Similarly, in the communication setting, what you could do is you have a communication channel. You want to decide what the transmission rate in the communication channel should be, so that I get some required delay or some waiting time is not that much of something, right? So since it's the first time, we'll slowly introduce what are performance measures and trade-offs. But once we have done the first stage, first 2 3 times, we'll do the same thing again and again. So basically, this whole class would be what are, if writing down your decision variables, writing down your known variables, writing down your cost function and cost functions. That is all the requirements, and then formatting it up as an objective function, and then giving it all the constraints that you need. And then once those constraints are given, we'll try to formulate it as an optimization problem. So you want to minimize your reward, or you want to maximize your reward, or you want to minimize your cost or something. We formulate as an optimization problem and try to find the optimal solution for it. That is the design part. The control part of it is we'll do the same thing but in a stochastic setting, where in the design part what we'll do is every parameter is fixed, but every parameter is fixed. We just want to work on parameters. In the design part, what we'll do is we'll do stochastic optimization, right? So we have optimization, stochastic optimization, design, just the normal optimization, uh, control, stochastic optimization, where you want to take decision at each and every step of your slot, right? Okay, so some performance measures and trade-offs. So tips are one of the most basic performance measures that we see are a number of customers in the system. Right. Next, we have waiting times of the customers. And then uh, we might, if your system runs for a long time, which we are doing in this case, you might be interested in some long run average or some expected steady state number, long run average of some delay, um, or waiting time or something else, right? Mm, all these are in some level they are measures of congestion. So what you want to measure in your queuing system is how congested your queuing system is. The more congested your queuing system is, the more bad design you have done. But you'll always find it as a trade-off between the design of the queuing system. In the design of the queuing system, you'll find a trade-off with saying that, okay, I have very less congestion. It could mean that you have over-designed and you're putting up more resources in the queuing system than you actually need to, or and if you have more congestion, it is a very bad design also. So you need this trade-off. So the trade-off is less resources you allocate. The less is when I mean that I've allocated less resources, that means that I'm giving a very less service rate. When I decrease service rate, you will see that the arrivals would clog up, right? And the queue would keep on getting congested. So queue congestion is bad. You don't want congestion. Queue congestion increases the waiting times of the customer, which would put more cost, and which would mm, 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 not allow more customers to come to your queuing system, right? And more service rate also incurs a cost because you've allocated more resources to just get the service rate. So you need to find the optimal service rate that you need to design so that your requirements are met, right? So now let's jump into a simple model with linear service rates and waiting cost, right? So we have linear service rates and waiting costs. So first we'll consider two types of costs. So the first cost is the service cost. So this is a rate type of cost, which is constant linear. Right? The second is waiting cost. This is also linear. Rate type, which is also linear with factor h, right? So what happens? So what do I mean when I say it is a service cost C is linear is if I choose mu as my service rate, then the cost that I paid to choose this is C into mu, right? C is some positive number. Okay. Yeah. And what I mean by waiting cost is H is if a customer waits for time t seconds, right? If he waits for time t seconds, then he pays H into t, right? This is a waiting cost. Okay. So the same thing you could write it as if in a unit time I customers wait in queue, then it is H into I, the total cost that the system occurs. So this is the total cost to the system. This is the cost to the customer, right? Now, since we are dealing with long-term average and steady state, so okay, so yeah, so since we are talking about long-term averages, right? So before that, the basic thing of queuing theory is you have your arrival rate and your service rate Q. A steady state exists only if your service rate is greater than your arrival. This implies that you have a steady state in your queue. If not, then your queue blows up to infinity and there is no steady state, right? So we'll always make an assumption that your service rate is greater than your arrival rate. And under this assumption, you'll get hit a service state. Now you have your costs. So you have your decision variables, you have your cost functions. Now we'll define an objective function based on this. So the objective function is C mu. This is equal to C into mu. Okay, sorry. K mu plus H into L mu. Now, what does this L mu mean? L mu is the expected number of expected number in the system. Right. So basically, since you are steady state and you have a long-term average, you take expectation of both these costs. Since C into mu is a constant and mu is just a number. So C into mu remains C into mu. H is a number, it comes out. The expected. So now you have this expectation of I. I is the number of things or customers in the system, and the expected number or customers in the system is suppose a function of mu, which is n, right? Now, most important. Now we'll use closed form solutions from MM1 from queuing theory to formulate our objective function. So from queuing theory, we know that M1 queues the expected number of customers in the system. That formula is given by lambda by mu minus lambda. Okay, so we'll digress here a bit. Okay, just give me 1 minute. We'll digress here and show how to derive this formula of expected number of customers. So since our M1, so coming back to the topic. So we have defined our objective function. The objective function, we have the service cost and the waiting cost. So this is service cost. This is the waiting cost. Or you can say this is the expected steady state total cost. So combining these all, the function that you have is the expected steady state total cost. Right now, how do you uh, derive this expected number of in a steady state? So since you have an MM1Q, MM1Q can basically be modeled as a birth death process. Okay, so I'll tell what about the process. The birth process, basically every arrival is modeled as a birth and every departure is modeled as a death. So when you have a birth, you have a new member coming into the queue. When you have a death or departure, you have an old member leaving away from the queue, right? But the MM1 queue, the rates are fixed, so they don't change according to the number of persons in the queue. They are same. So suppose you have 0 members in the queue, right? With rate lambda, this rate, not probability, with rate lambda, one new person would arrive, right? But if there is one person in the queue with rate mu, one new person will die in the sense that he'll leave the queue. Similarly, with rate lambda, you go from 1 to 2, and with rate mu, you come from 1 to 2. This goes on. And suppose you have n minus 1 and n, right? Lambda, mu, lambda, n plus 1. This is your mu. And this goes on to infinity, right? This is your chain. So this is your CTMC. So this is CTMC. Okay. So now you need to derive some equations. So basically what we want to find out first is, so our ultimate goal is to find the expected number of customers. Okay, let me call them customers in the system, right? This zero, this states number in the system. Similarly, this states number in the system. So all the numbers inside the circle, they state the number in the system, right? So now, as you can see, you have infinite. It could be infinity, right? It could be any number. It could be in the. So now, to find the expectation, what you need to find is first the probability distribution of all these states. So you need to find you need to find PNs, right? You need to find P0, you need to find P1, P2, P3, so on, and then you need to find summation of NPN. If you find out those three, so summation NPN, this gives you the expected number of customers in the system, or basically your L mu lambda, or however you parameterize it. So the main trick here is to find the probability distribution of the states, right? So there are multiple ways you can do this. I'll give you 2 ways, maybe 3. Okay, so let's see. So first, what we'll try to do is we'll do the iterative. This is one of the most intuitive thing that you can do. So you have two things you can write balance equations for. So you have a barrier equation and you have a balance equation, right? So the barrier equation is given by you have this barrier between two states and your flow across. So flows that so the barrier cuts the there are two crossings across that barrier, right? Now the rates of those two should be equal. So flow going one way of that barrier should be equal to the flow coming out from that barrier, right? So the flow going one way is this, right? But then you're at state one. So you will find yourself in state 1 with probability P1, right? So P1 is a probability that there is only one customer in the queue. And with rate lambda, you go from 1 to 2, right? So P1 into lambda equal to, similarly, P2 is the probability that you find yourself at state 2. So probability that there are only two customers in the queue. And then with rate mu, you go to state 2. This is equal to P2 into mu, right? So similarly, you write Barré equation across this. You are at P0, P lambda, P1, mu, right? So you have P0 lambda equal to P1 mu, which implies P1 equal to P0 lambda by mu, right? Now you iterate this. So you have this. Okay, so P2 equal to P1 into lambda by mu. But you know P1 equal to P0 lambda mu. So this becomes P0 lambda square by mu square, right? Now you keep on iterating this at each and every time. You do keep on iterating this for each and every barrier equation that you write. You will see that every barrier equation has the same form. So you'll get Pn minus 1 into lambda equal to Pn into mu. Pn equal to Pn minus 1 lambda by mu. Pn minus 1 you can write it as P0 into lambda by mu whole power n minus 1 into lambda by mu. This becomes P0 lambda by mu whole power n, right? But now you have to find P0. We don't know what P0 is. You have found Pn. So give me any Pn, I'll give you it in terms of P0. But now how do you find P0? So one basic thing you could use is the property of distributions that we already know. So we know that any distribution, since Pn is a distribution, so n belongs to n, Pn, this sums up to 1, right? Okay, so now I'll n equal to 0 to infinity. I'll replace this with mu. So I will not use n, I'll use I whole power I. This sums up to it, right? P0 doesn't depend on the summation. I can bring the P0 out. Summation I equal to 0 to infinity. Lambda by mu power I is equal to 1, which implies P0. Now, as you can see, if I expand this, I'll get 1 lambda plus mu lambda by mu whole square plus 1. This is a GP series. This is a GP series. Therefore, sum of GP series is 1 by 1 minus R. R here is lambda by mu. This equal to 1, which implies P0 equal to mu minus lambda by mu, right? So you have found what P0 is. So all this lambda by mu terms getting confusing. So what I'll do is I'll introduce a new term. I'll introduce a term I will call as rho lambda by mu. Okay. This rho goes by many names. I'll call it utilization factor. Okay. Uh, this is basically less than 1. So it is a number between 0 and 1. It's a fraction. Um, and yeah, so whenever we'll see that this mu minus lambda by mu or so we'll interswitch between uh, functions in terms of rho or functions in terms of we'll interchange the objective functions either as a function of mu and lambda or as function of rho wherever we see. So here we've got P0 equal to mu minus lambda. That means that P0 equal to, in terms of rho, it's 1 minus rho. Easy to write, 1 minus rho. Then writing mu minus lambda by b. Okay. So now, okay, now we want to write Pn. Okay. Pn is P0. First, let's write here. Sorry. Pn is P0 into lambda by mu whole power n, right? So it will become mu minus lambda into lambda power n by mu power n plus 1. So writing all this, we will try to write it in terms of rho. Okay. So when I try to write it in terms of rho, Pn equal to 1 minus rho in rho power n. Now, as you can see, the distribution here, it resembles the geometric distribution, right? So geometric distribution is something which is a discrete distribution where you have successive failures and then a first success. So 1 minus 1 is a probability in which you fail, you have success. So this is your success probability, is your failure probability, right? So you fail n times, you fail n minus 1 times, and then you get success at nth time. Yeah. So that is geometric distribution. And now the expectation of geometric distribution L in terms of rho. Okay, so you have a random variable whose probability distribution you have found, which is basically the number of, so you have found the probability distribution of number of customers in the system. So Pn is the distribution of number of customers in the system. Now we have shown that this is geometric distribution. And you need to find the expected number of customers. So it's basically you have a random variable which follows the geometric distribution. Now the expectation of the random variable is rho by failure probability by success probability. Rho by 1 minus rho. Right. So this becomes lambda by mu by 1 minus lambda by mu, which is equal to lambda by mu minus lambda. Well, that is what we have written, stated here, right? This is how you, this one method, the iteration method, where you use barrier functions to iterate over states and find the. Okay, so we can do the same with generating functions, but it is actually a long process. I'll skip the second and third methods, right? You can do the same thing. You'll reach the same conclusion using generating functions, right? You can use sequences, some specific sequences. This is the discrete type evolution. Oh yeah, no, difference equations, difference equations. You can use any of them to get what you are going to get. Um, okay, I'll just introduce one more. Here we balanced barrier functions. There is one more type where you balance equations. That is the state balance equations. That is also important. So let me tell you what that is. So I'll draw the same Markov chain again. So you have state 0, state 1, state 2, so on, n minus 1, n plus 1, so on, right? 0 to 1 with lambda, 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 mu, mu. Okay, so the flow equations should also be satisfied at each state. So if you're looking at state n, then the flow entering state n and the flow going away from state n, the rate should be equal. So when I say the rate should be equal, I mean, so you're at state n, Pn, There are two flows that are going away from N. One is mu, so one is mu, and one is lambda, right? So Pn into lambda plus mu. This should be equal to the states coming into state N. So you are at Pn plus 1 into mu plus Pn minus 1 into lambda. So your whole balance equation would become Pn into lambda plus mu equal to Pn plus 1 into mu plus Pn minus 1 lambda. So we basically write in terms of Pn plus 1. So Pn plus 1 becomes Pn into lambda plus mu by mu minus Pn minus 1 lambda by mu. Right, this becomes Pn into rho plus 1 minus Pn minus 1 into rho. And similarly, if you write the balance equation at node 0, you have P0 into uh, you are going away with state lambda equal to P1 into mu. And coming back. So you have this equation and this equation, Pn plus 1, right? Where you have P1 equal to P naught into rho. So this is your first equation, this is your second equation. Yeah, okay, and then you use generating function. So generating function, okay, so then you have to define what generating functions are. Mm, yeah, okay, I'll skip that. The other methods where you derive the same equation, LP equal to lambda by mu minus lambda. You can use generating functions, you can use difference equations also. But for using generating function differential equations, you need to write these kind of balance equations, not the barrier equation, the balance equations. Okay. Yeah, too much of progress. We'll come back to the problem. The problem we had today was we had a cost function k mu, which is equal to c into mu plus h into lambda by mu minus lambda. This is your expected cost attribute. So what we want to do is we want to find minimum mu greater than lambda such that c into mu plus h into lambda by mu minus lambda. We need to minimize this. Okay, this is the cost function that we minimize such that mu is greater than lambda. That is our assumption. Because if mu is less than lambda, then this does not hold. This does not hold for mu less than lambda. Okay. Now in the optimization below, first what you do is treat this as your cost function. You find the derivative with respect to mu. You get c minus h lambda by mu minus lambda whole square. Right. Okay. So next what we'll do is we find the second derivative also. So that just to check whether uh, this is a convex optimized polynomial. So we'll get 2h lambda by mu minus lambda whole cube. And since you have the constant mu is greater than lambda, this is greater than 0. So 2h lambda, h is a positive number, lambda is a positive number. So this is greater than 0. For the case mu is greater than lambda. Therefore, we have convex optimized polynomial. So what here it means is the rate of change of the gradient is always positive. So if you have a gradient, the gradient always keeps on increasing, right, as you go forward. That is what this being greater than 0 means. So you have a convex function and you'll always be able to find the minimum at the point where the gradient is 0, right? But it'll only be the minimum if you have a convex function. Okay. So what we have to do is we have to find k prime mu equal to 0, which implies c minus h lambda by mu minus lambda whole square equal to 0, which is equal to, now you need to find mu. Mu is additional variable. All the other variables you know. Create mu minus lambda whole square equal to h lambda by c. Mu equal to lambda plus root h lambda by c. So this is your, so I'll name it mu star, optimal mu at which it happens. Okay. So this is your optimal. Yeah. Okay. So if I draw a diagram between your service rate and cost, cost in the sense the total cost function. So my service cost per service rate, it is linear, right? So it will keep on increasing. Okay. As service rate increases, the cost will increase. Okay. But cost of waiting, it will decrease. Now, how will it decrease? It will decrease lambda by mu minus lambda. So if you increase mu, and we know that mu is greater than lambda, so you have lambda somewhere here and mu somewhere here. Keep on increasing mu, this lower term increases. Lower term increases, this whole term decreases. So it's 1 by x kind of thing. And you can't have mu less than lambda. So you'll have your lambda somewhere here. And at lambda, if mu is lambda, then this term is infinite, right? This will go to infinity. So this, so you have a line here. Okay? And then so this is your service cost. This is your waiting cost. Okay? And the total cost would also be something like this. We have a total cost. Okay. So initially the waiting cost would dominate, then the service cost would dominate. At the point where, so the diagram would be something like this, right? So at the point where these two meet is where you'll find the optimal. This is the total cost. Total cost basically adding up service cost and waiting cost levels, and then you get the optimal. And wheels, okay, in the so this is your new step, optimal that you need to fix so that you have a very less waiting cost. So any less mu than mu star will have a very huge waiting cost. Any more, any mu greater than mu star is, you'll not see that much of an improvement in the waiting cost, but then you have to pay huge amount of service cost because you're allocating more resources, right? Okay. That is the basic idea of the trade-off that we were talking about. So now since you have the optimal service cost, we'll try to plug this back into the cost function into k mu. So we'll try to calculate k mu star. So k mu star is c into lambda plus root h lambda by c plus h into lambda by lambda plus root h lambda by c minus lambda. This is equal to c lambda plus root h c lambda plus another root h c lambda. Okay. So this is your total. This is your k mu star. This has a interpretation is this is the minimum cost that you at least have to provide. You have to provide C lambda. Your mu should be greater than lambda. So that is the minimum cost that you're providing. And then the next two terms represent the this is the basic minimum cost you have to provide. This term is the service cost, and this is the waiting cost. Right. Now here what happens is both the terms are root lambda hc, right? The service cost and the waiting cost. So what the optimization problem sees is it sees an optimization problem. Where is the optimization problem? Yeah, here. So it is a constraint which says that you at least have to provide lambda amount of service and then sees two costs. One is C mu and one is H lambda by mu minus lambda. What it does is it equates these two costs, which normally doesn't happen, but okay. So what we'll try to see is, so we'll see this and we'll close for today. Okay, so we'll let us see how much surplus we are giving. So you would be fine if you give lambda as a something just greater than lambda as your service rate, but then you would see huge amount of waiting cost, which you don't want, right? So we want to see how far away mu star is from lambda. So we want to see mu star minus lambda. Okay. So now let us reformulate the whole problem so that we can see how far away mu star is from lambda with introducing a new variable mu tilde, where mu tilde is mu minus lambda. Okay. And now it's the same cost function, but written differently. Mu tilde, this is C into mu tilde plus H lambda by mu tilde. Oh, sorry. So this is, which implies mu equal to mu tilde plus lambda. Okay, so now I will write C as a function of mu tilde. This will become C into mu tilde plus lambda plus H into lambda by mu tilde plus lambda minus lambda. This is equal to C into mu tilde plus C into lambda plus H into lambda by mu tilde. Now see the decision variable is mu tilde. It's not C lambda. So this middle term, it has no bearing on whatever decision you take. C lambda is always going to be there. So this C lambda is similar to the basic minimum cost that you have provided here, right? So if I can just take out this C lambda and minimize this term, it is the same as minimizing the whole term because C lambda is just a constant, right? So now I introduce C tilde mu tilde, which is C into mu tilde plus H lambda by mu tilde. I need to minimize this new cost function, right? Where my new variable is mu minus lambda, but not mu. This is k mu tilde, k tilde. Okay. So again, minimize K tilde, mu tilde, such that mu tilde is greater than 0. If mu tilde is mu minus lambda should be greater than 0. That is a constraint that I had from the starting. Otherwise, no steady state. Otherwise, Q will not reach steady state. If Q doesn't reach steady state, then your Q will blow up. There is no point in calculating minimizing the waiting costs. Right? Okay. So K tilde prime mu tilde. This will become C minus H lambda by mu tilde square. Again, find the second derivatives. We get 2H lambda by mu tilde cube. Now the constant mu tilde greater than 0. This greater than 0, this greater than 0, this greater than 0. Therefore, we are again in the region of convex optimization bound. Right? So we are in the region constant. Now the optimal solution is seen when K tilde equal to 0, which implies C equal to H lambda by mu tilde square, which implies mu tilde equal to root H lambda by C. And we calculate at mu tilde star the cost function. You get root HC lambda plus root HC lambda. So the particular structure that we see here is this cost function is basically that the sum of a term is proportional to the decision variable and a term is proportional to the reciprocal, right? Because you have some one sum, this is proportional to decision variable, this reciprocal to decision variable. So this leads to property that the optimal solution, what it does, it's equate these two terms. So your optimal solution would be C mu tilde equal to H lambda by mu. So you get mu tilde equal to root H lambda by C, unit plus R, right? But this is not the case for any general minimizing two sum. Only if it is directly proportional and inversely proportional. It happens here. So the general condition is the marginal increase in the first term should be equal to the marginal decrease in the second term. So one term is increasing, the other term is decreasing. Here it's just a direct linear proportional in the first term and inverse proportional in the second term with no other things. But if you have some other things, then the problem becomes more complicated, right? Okay. So yeah. So what we'll do is, okay, I'll just do a 5-minute recap of what we have done today. Um, basically today was an introduction class on how to design optimal queuing systems. So we introduced what a queue is. We showed optimal design of queuing systems. What is a decision variable? What are cost and benefits? What is an objective function? Right. Uh, uh, mm, then what we did was we fixed the queuing principle, and then we fixed the arrival to the queuing principle. We wanted to find the service rate such that some cost is minimized or some effective cost is there. So the cost that we worked for today is service cost and waiting cost. We formed the objective function. Now the objective function was formed in a long-term average expectation. Okay. So basically, we again got back to queuing systems and calculated what the expected number of customers I see in that day using the MM1 model, which is modeled as a budget process. And calculate that expectation. We we wrote out the objective function. We found we showed that it is in convex optimized problem, so it will have a global minima. And then we found the global minima, and we intuitively showed using graph where to find that local minima. We showed some intuition on how to find that local minima. So this is basically how the class would go. We'll try to define what the decision variables are, what type of queue I'm using, what are the parameters in the queue, how do I model them all using the mathematical model. We'll define cost functions, what are the parameters that I'm looking to optimize. Then we'll define the objective function. How can I bring all those together? How can I bring all the costs into one objective function? And then we'll try to solve it's a complex optimization problem. It might not always be a complex optimization problem. Then we'll have to use different methods to come up with solutions to those methods, right? Uh, yeah. So we'll stop the class for today here. Next class, we'll see some more extensions on mm, optimal service rate. Then we'll go to optimal arrival rate. Then we'll see what happens if we do both, if we make both of them as decision variable. So arrival rate and service rate. What happens if I change? So here I've taken linear mm, functions. What happens if I don't use linear functions? Yeah, we'll see some variations in service. And then we'll see arrivals. Then we'll see both. Then we'll see different queuing models. How does it change? Done. Okay. So I will stop the